Hey guys, this is Math 148, section 13.2, and this is me! I'm kidding. This is Bernhard Riemann, and he was a German, Bernhard Riemann. He was a German mathematician working in the 1850s, and he came up with the fundamental theorem of calculus, or he was instrumental in coming up with it. And this is what we are studying in section 13.2, and I think this is actually really cool, and I'm really just blown away and impressed that anybody came up with it. So, before, in section 13.1, we were looking at a curve like this one. This is y equals x cubed, and trying to estimate the area under the curve. So let's say we wanted the area from x equals 2 to x equals 3. And we said, what's the area? Well, in 13.2, we were estimating the area by finding these boxes and approximating the area with boxes. But in this section, sorry, in 13.1 we used the boxes. In 13.2, we're saying we can use the fundamental theorem of calculus developed by this guy who expanded these box ideas into something that we call the Riemann sum. And you don't have to worry too much about this for the purposes of this class, but you do need to know this, the fundamental theorem of calculus. So let f be a continuous function on the interval a to b. Then the definite interval of f exists on this interval. And here's the big exciting thing. The integral from a to b, you read this, you start at the bottom. So you say from a to b of f of x equals big F of a b minus big F of a, where big F, if you take the derivative of big F, it equals little f. So what this is saying is that we can use the interval to essentially find the areas under the curve. Now the area under the curve thing is a little bit tricky, and I'll explain that in a second, but essentially we're going to use the integral then to find these regions under the curve. So this is how it works. This is question number 5. So you're going to have lots of problems that ask you to evaluate the definite integral. This is what a definite integral looks like. From 2 to 4, you start on the bottom, from 2 to 4 of x cubed dx. This is question number 5. Okay? The part that makes this definite, you'll notice there's little 2's here. Before there was nothing there. Because we have numbers, we call these a definite integral. We are trying to define exactly a specific region or part of the function. So this is a definite interval. And the way you solve these is you first take the integral, and then we're going to plug in the endpoints. So we're going to use the fundamental theorem of calculus. First we're going to take the integral, then we're going to take the integral evaluated at b minus a. So I will show you how this works. Wait, where's my, here. So first take the integral. Well, the integral of this is 1/4 x to the 4th plus the constant. Okay, so step 1, take the integral. Boy, that does not show up on the white. Okay, step 2, I'll turn to red. Evaluate the integral at, I'll say, f of b, and then you subtract at f of a. And remember, b is the top end point, and a is the bottom. A is on bottom. Okay. So, in this case, and then you draw a line here. The way you do this notation is you say going, or you could 4 to 2, or 2 to 4. So first we plug in x equals 4, and this is what we get. 1/4 times 4 to the 4th plus a constant. This is the sort of f of 4 part. F of 4 minus, now we're going to plug in x equals 2, so I get 1/4 times 2, that's supposed to be a 2 to the 4th plus a constant. Okay, this part here is the f of 2, so you're just plugging in, basically just plugging in 4, subtract, plug in 2, and you subtract it. So when you plug in 4, you get 64. I'll switch to blue. So this whole piece evaluated at 4 is 64 minus this whole piece evaluated at 2 is 4. So when you plug in x equals 2 there, you get 4. So your answer is 60 minus 4, which is 60. So what that's telling us is that this curve y equals x cubed. Here's the curve. I plugged it into the graphing calculator. Evaluating it from 2 to 4. I can't draw the line. Okay. This whole area under the curve, don't care about that Adobe update. The whole area under the curve is equal to 60. And that is pretty cool and powerful. So that's why I am impressed with this guy, Riemann. Way to go, Riemann. Let's look at another one of these problems. And this will illustrate to you that we're not exclusively finding the area under the curve, so I have to be careful to describe to you the difference here. So the problem says evaluate this definite integral, and you're going to have lots of these problems on your homework and on the test. 10 minus 4x dx. Okay, step 1, just find the integral. And I forgot to mention the integration constant. It goes away. I'll show you what I mean in this problem. So in this case, step 1, find the integral. So you'll notice that these definite integral endpoints are here, but for the beginning of the problem, just ignore them and don't worry about them. So you take 10 times x minus 4 times, you add 1 here to get the exponent, x squared divided by 2, you'd say plus some constant of integration. Okay, that gives us 10x minus 2x squared plus the constant of integration. So that's the integral. Now we go back and pick up the endpoints. We're evaluating it from 4, or from 1 to 4. Make sure that's right. 1 to 4. So first we're going to plug in 4. So we have 10 times 4 minus 2 times 4 squared. And I should have done this on the last problem. You can add the constant of integration there if you want. But you'll see, now we're plugging in 1. 10 times 1 minus 2 times 1 squared plus a constant. The constants are always going to cancel each other out, so you really don't have to worry about them. When you see these endpoints, you don't really have to include the constant of integration. So, in this case, this whole piece is equal to 8 minus this whole piece equals 8. Actually, it would be 8 plus a constant minus a constant. So again, for the definite integrals, if you see endpoints, you don't really have to worry about the constant of integration. This tells us, that this integral, the value is 0. But Kate, you said integrals were the area under the curve. How can an area equal 0? Okay, well, I was both right and a little bit wrong. So here's this equation. Question number 9. This is the equation y, just change, equals 10 minus 4x. It's a line, as you can see. You recognize that from here. So what we're saying is from 1 to 4, down here, the integral represents this region. So they're careful not to say area. It's more of a region. And technically, it's only finding the area above the x-axis. So in our case, we have part of the region is above the x-axis and part of the region is below the x-axis. Do you see that? That's above and that's below. So the areas cancel each other out and you end up with this integral. I'm using the word area because it's not strictly an area because mathematicians don't like to have areas that are equal to 0. So that the integral equals 0. So actually, you're only finding the area of the curve. So it is only the area if you're talking about a region that's above the x-axis. So you're only finding the true area of the curve if the function is like greater than 0, if it's above the axis. Otherwise you get these negative values. Anytime you have the function below the curve, the integral of f of x is going to be negative. So if you get a negative integral, that tells you it has a region below the curve. So I personally, like from my personal intuition, don't really mind thinking of this as positive area and this is negative area, but I can understand that mathematically that doesn't make any sense, so I should not be using the word area. We should say regions above and regions below. Ugh, to be so picky. All right. So here's another question. This is an application. This is question number 57, and I have it here written down. So, you, my friends, have just purchased an oil change service franchise. Lucky you, you bought a Jiffy Lube or an oil chain Henry's or oil can Henry's. Is that what that is? And you've decided that your income stream is flowing continuously at an annual rate given by this function. So this function, f of t equals 10,000 e to the 0.02 t, represents your income from your Jiffy Lube or whatever you have. Find the total income of this chain over the first 2 years. So finding total income means we are finding the derivative, the area under the curve. So what you want to do to solve this problem is we're going to find the area from 0 to 2 of our function, 10,000 e to the 0.02, I should say 0.02 t dt. This is going to represent the income for the first 2 years. How would you know to take the integral? Well, you might not. That's why I'm doing this problem. Jeepers. Okay. So, step 1, you're going to look at this problem and you go, oh, okay, it's a definite integral. I don't have to worry about the constant of integration. But don't worry about that right now. Focus first on the integral and just do the integration like we did in chapter 12. So you can say this is the integral. Sure, 0 to 2, we'll leave that there. 10,000. And now we have this e to the 0.02 t dt. So remember, with these e to the something, we're going to use our u substitution because we want this to be a pure variable. We don't like this 0.02 part. So we're going to let u equal 0.02 t, and do u substitution. Du is equal to 0.02 dt. So this tells us on this side we want to add a 0.02 there so that it will be beautiful and perfect and we can take the integration. But we can't just multiply a 0.02 here, and it changes it, so we have to divide by 0.02 also. Again, this is chapter 12 stuff. You're like, but chapter 12 is hard. It was hard. It's tough. We're doing it again here. It's still tough. This part here, 10,000 divided by 0.02 becomes 500,000. Like that. And this part here, I'm just going to leave the 0 and 2 here. It's not technically correct. I should be changing them, but you just don't worry about the endpoints right now. This, now it's perfect in our formation. This becomes e to the u because that's e to the u, and O2 and dt, those cancel. Again, this is chapter 12. So this whole thing becomes 500,000 times e to the u plus our constant of integration. But now we have to substitute the u back. So we get 500,000 e to the 0.02 t, and then you can do plus a constant. Doesn't really matter if you include the constant or not. So now all we've done is take the integral. So now we have to deal with these endpoints. I'm going to go back to yellow. It's brighter. So you have 2 and 0. So we're going to start at 2, and you plug in 2 to start with. So we get 500,000 times e to the 0.02 times 2, like that, plus a constant if you want, minus 500,000 times e to the 0.02 times 0 plus the constant of integration, but you get plus, minus, they're going to go away. So this whole thing equals, this is 500,000, I'm going to go to a new page, 500,000 times e to the 0.04 minus, this other side just becomes 500,000. I'll show you why. Let's go back here. Because this is 1. That's just 1. So you have 500,000 times e to the 0.04 times minus 500,000. Ah, just easy breezy. You could practically do this one in your head, right? You would get 520,405 and 38 cents. If you could do that in your head, I would put you on TV or something. I'd make a vine of you. Okay, so now our answer is 20,405.39. which is actually the correct answer. But frankly, for 2 years of income, I don't know. I'm less than impressed. That's why I'm giving you this flat face. You got 2 years of income and you're making $20,000. Like your income that you're bringing in, not your profit, is $20,000. I think you guys should open a Subway and maybe skip the oil can Henrys. So the point, though, of all this is the real meat of these problems is you're going to take these integrals and you're going to say evaluate it at the top point minus the bottom point to find the integral. And for the most part, if your graph is above 0, then your integral is the area of the curve. And if you're in statistics, or if you've ever taken statistics, this is very exciting because here, right here, this is the equation of the normal z curve. This is a z curve, and this is what we do in statistics when you're taking calculus statistics, is you can just take the integral of this curve and prove that the area under the curve from 2, there, 2, 2, 2, to negative 2 to 2, that area is the probability, which is also 0.95. So in statistics, we did a lot of integration with these definite integrals to find probabilities. So what's the probability that the z is between 0 and 2? Well, whatever it is. So roughly 45% or something. Anyway, it's my stomping ground. I love definite integrals, so let me know if you guys have questions.